The game of Snow Snake is traditionally a Haudenosaunee winter game played by the men of the tribe after coming home from a hunting trip. The competition was between different villages in the Haudenosaunee tribe. Although the game was used to showcase each village's athletic ability, it was also used to boost the morale of the Haudenosaunee people during the long, cold winters. Traditionally, the game Snow Snake was a male-exclusive sport, and much like lacrosse, the women in the tribe were not allowed to touch the snow snake or watch the game being played. The game of Snow Snake is comprised of two main materials, a snow snake and a snow snake track. The snow snake is traditionally a piece of wood carved out of hickory ash. A snow snake can either be short, measuring just 3 feet, or long, measuring 6 feet. The snow snake is designed to be curved at one end and notched at the other, making it easier for the player to hold and throw the snow snake. A track is also needed to play Snow Snake. Snow must be piled to a height of 4 feet. Then, by using a log, players will drag the log through the 4-foot tall snow until a divot of about 5 inches in diameter is created in the snow. In addition, the track slowly slopes downwards to help the snake travel across the snow. To start playing, players will stand behind the track. They will grasp the snow snake with their dominant hand at the notch of the snow snake and non-dominant hand at the bottom of the snow snake, just supporting the weight. Players will perform a run-up to the track, and just before reaching the track will throw the snow snake in an underhand motion with the dominant top hand doing most of the work. Players will try to release the snow snake as parallel to the track as possible so the curved front end does not get stuck in the snow. Once the snow snake comes to a stop, the distance will be measured from the curved part of the snow snake to the start of the track. In a traditional game of Snow Snake, there are 4 teams, with no specific number of players on each team. The game is divided into rounds. Each round, teams will take turns throwing their snow snakes until each team has had 4 throws. The team who threw their snow snake the furthest in that round will receive 2 points for his team. The second furthest throw will receive a point for their team as well. Before the game starts, teams will predetermine the amount of points they will play up to. Usually a number of points is 7 or 11, but games can go longer. There are 2 main positions on a snow snake team. The first position is the player, who is responsible for throwing the snow snake along the snow track as far as possible. The second position is the goaler, who has the responsibility of maintaining the snow snakes during the actual game, and also has the responsibility of selecting what snow snake the player will use to perform his next throw.
When throwing a snow snake, the main goal is to release the snow snake with as great of a resultant velocity as possible, so that the snake can travel as far as possible. There are 2 main ways to release the snow snake with as great resultant velocity as possible. The first way is to increase the resultant velocity of the throw by having the thrower run at a greater velocity before the throw. When the snake is being thrown, the thrower is running at a velocity of 2.247 meters per second. Then we know that the resultant velocity of the snake after the throw is 9.066 meters per second, which means that the snake in relation to the thrower has a velocity of 6.639 meters per second. What this means is if the velocity of the snake in relation to the thrower remains constant at 6.639 meters per second, then one of the easiest ways to increase the resultant velocity is by having a larger run-up before the throw. As seen with the equation, velocity of snake in relation to thrower plus velocity of thrower in relation to ground equals velocity of snake in relation to ground. The other potential factor that could increase the resultant velocity is the velocity of the snake in relation to the thrower. For this analysis, we will refer to a different equation, change in velocity. As the snake starts the acceleration, the runner has given the snow snake an initial velocity of 2.247 meters per second. Then at the end of the acceleration applied by the thrower, the snake has a velocity of 9.066 meters per second. Using the equation, change in velocity equals v2 minus v1, we know that the snake's change in velocity was 6.639 meters per second forwards, which happens to be the same value as the velocity of the snake in relation to the thrower. Going a bit further with this calculation, now that we have the change in velocity of the snake, by dividing it by the time of acceleration, we get the acceleration of the snow snake to be 31.17 meters per second squared. Through the equations, we see that the other ways to maximize resultant velocity of the snake is by increasing the change in velocity and with it the acceleration of the snow snake. Since the snow snake glides along the track, the snake will not follow a parabolic path. During the acceleration applied by the thrower, the snake has two primary forces acting on it, a force of application and the force of gravity acting downwards. The goal of Snow Snake is to launch the snake parallel to the track. In order to do this, the force of application will have a vertical component upwards to cancel out the effect of gravity on the snake. Using the components of the force of application, we can find out the magnitude of the force of application on the snake using data from previous kinematics calculations. After the snow snake is released, the snake no longer has a force of application on the snake, but three primary forces now acting on it: the force of gravity, the force of the normal, and the force of kinetic friction. Since the snake is on a downwards ramp, this will incorporate several fictitious forces. A fictitious force is a force that is used to describe the forces in a non-inertial frame of reference. This includes an accelerated frame of reference and a rotated frame of reference. As we break the forces acting on the snow snake into components, we see that there is a portion of the force of gravity that has the same magnitude as the force of normal, and another component that is fictitious that applies a force on the snow snake down the ramp. When all the forces are added together, we can calculate the acceleration of the snake. As the force of kinetic friction will be greater than the horizontal component of the force of gravity, the snake will keep accelerating backwards, or slowing down, as it travels along the track. Using this acceleration, we can then calculate the estimated displacement of the snake. For this calculation, it assumes the snake is constantly traveling down the ramp. However, oftentimes the snake will either hit the sides of the track, causing it to slow down at a faster rate. If the snake is able to travel down the whole ramp, eventually the track will level out, causing the force of kinetic friction to increase. Using the angle on the ramp, 5 degrees, and the height of the ramp, 0.91 meters, we can then estimate the distance that the snake will be traveling down the ramp. Using this distance, we can then calculate the snake's velocity after it has slid all the way down the ramp, to be 8.924782.904 meters per second. Once we have the velocity when the ramp levels out, we can then get the acceleration of the snake when the ramp levels out. With the second acceleration, we can calculate the snake's displacement at a level track to be 40.6 meters. Through these calculations, we get the snake's total displacement to be 51 meters, which is a realistic displacement for a real game of snow snake. One other element that could be incorporated into the throw of the snow snake would be the torque produced by the thrower. Torque is expressed through the equation T equals Fap times R, where T is torque, Fap is the force of application, and R is the radial distance. In this case, the thrower's arm is 0.71 meters long, and using the previously established magnitude of the force of application, we find that the thrower produces a torque of 4.8 joules. If the team wishes to produce the most torque on the throw, there are two ways to improve this measure. One, improve the force of application, or the other option is to let the person with the longest arm throw the snow snake. By doing this, you allow for the thrower to produce the same amount of work with less force applied, thus giving the thrower a greater mechanical advantage. With our example, the thrower has an arm length of 0.71 meters, but if the thrower were to have a longer arm, then the thrower could produce more torque during the throw, assuming the force applied remains constant. The previous estimated value of 51 meters as a total displacement of the snow snake is assuming ideal conditions, but this will not always be the reality for the snake. As the snake travels along the track, it will have several collisions with the sides of the track and the snow in the middle of the track. When the snow snake collides with the sides of the track, since momentum is always conserved in collisions, some of the snake's momentum will be transferred to the track, causing the snake to lose momentum every time it hits the ramp. The snow snake will also experience perfectly inelastic collisions as snow sticks to the snake. A perfectly inelastic collision is a collision where the greatest possible amount of kinetic energy will be lost. So the snake will lose a considerable amount of velocity as it sticks to more snow. When the snake is thrown, the amplitude of the force of application is 6.8 newtons, and the time during the acceleration is 0.2130 seconds. This means that the snake experienced an impulse of 1.44 newton-seconds upon release. Also at release, since the initial velocity of the snake is 9.066 meters per second, this means that the snow snake has an initial momentum of 1.89 kilogram meters per second. One other thing that we can find out in terms of energy is the energy lost due to work of friction on the ramp. When the snake is released, it has both kinetic energy and gravitational potential energy. Then as it travels down the ramp, it loses energy due to work of friction. When the snake finally reaches the bottom of the ramp, it will have exclusively kinetic energy. Knowing this, we can establish that the energy lost due to work of friction is equal to the kinetic energy plus the gravitational energy minus the final kinetic energy. After calculations, we get the energy lost due to work of friction on the ramp to be approximately 2.1 joules.
For interplanetary play, we have decided to use Jupiter and the Moon as our two planets of choice. For our calculations, we only assumed that we were sending our snow snake up to the planet, since we assumed the aliens would be able to play the game from there and only require the stick. For the Moon, we decided to calculate the change in gravitational potential energy in order to reach the Moon. We found that the Moon lies about 384,400 kilometers from the Earth. We also already know the gravitational constant, the mass of Earth, the radii of Earth, and the mass of the snow snake. By using this information, we were able to find that the change in gravitational potential energy was negative 12,791,477.89 joules. We also found the potential gravitational energy on the Moon. By using the mass of the Moon, the gravitational constant, the mass of the stick, and the radius of the Moon, we were able to define that the potential gravitational energy on the Moon is negative 595,748.7059 joules. We then calculated the change in gravitational potential energy on Jupiter. Jupiter is approximately 918 million kilometers away from Earth. We found that the change in potential gravitational energy was negative 13,003,691.45 joules. Then we found that the amount of potential gravitational energy on Jupiter was negative 376,569,142.9 joules. For true interplanetary play, we then want to calculate the amount of kinetic energy and speed that was required to take this game out of this world. For an object to escape Earth's gravitational field, the total energy has to be zero. This means that the absolute value of Earth's gravitational potential energy is equal to the kinetic energy. We then found the speed required to escape Earth's field as 11,181.9 meters per second. We then calculated the difference in magnetic force on these planets. For all calculations, we assumed our initial launch velocity was consistent at 9.066 meters per second, and our snow snake was always charged at negative 5 times 10 to the negative 5 coulombs. We found that Earth has a magnetic field of 5 times 10 to the negative 5 teslas, the Moon has a magnetic field strength of 5.0 times 10 to the negative 6 teslas, and Jupiter has a magnetic field strength of 7.0 times 10 to the negative 4 teslas. When doing our calculations, we found that magnetic force on all planets was very small, therefore wouldn't affect how our game was played drastically. On the Moon, there is less gravity than compared to Earth. This would affect our game because less gravity would mean the snow snake would slide for a longer distance and would not have similar results to the game on Earth. To try and model this game after the Earth version as closely as possible, we would need to add a force in the downward direction. This is because the downward force of gravity is less, the upward force of the normal is less, and the force of friction is less. We can add a greater downward force by incorporating an electric field. By adding an electric field with the same charge of the snow stick on the top and a different charge on the bottom, we can recreate an Earth-like atmosphere. We found that the difference in gravitational force between the Earth and the Moon on our snow snake was 1.7004 newtons. We decided to put a positively charged plate at the bottom of the snow snake track and a negatively charged plate at the top. The potential difference between these plates is 34,000 volts, and the plates were spaced a meter apart. We had to find the charge to put on the snow snake. We found that by giving the snow snake a charge of negative 5 times 10 to the negative 5 coulombs, it would best replicate Earth playing like conditions. Due to wood being a bit of an insulator, we had to rub a cloth on the snow snake to give it its negative charge. Jupiter, however, has more gravity than Earth. Therefore, the downward force of gravity is greater. The force of normal is also greater, and in turn, the force of friction is larger. We calculated that Jupiter had 3.3696 newtons more gravity acting on our snow snake than Earth. This means that playing this game on Jupiter would be tough because the snow snake really wouldn't go too far. So, we used our same parallel plates as before, with a positively charged plate at the bottom and negatively charged at the top, 1 meter apart with a potential difference of 34,000 volts. However, this time we found that the snow snake required to have a charge of 9.9 times 10 to the negative 5 coulombs. So we charged by friction again, except this time rubbed a different cloth on the snow snake, giving it a positive charge.